Neutrons are very complementary to X-ray probes because of their different scattering amplitudes. For example, in a calculator, X-rays mostly see the wires made of heavy metallic atoms, whereas neutrons mostly see the plastic parts, full of hydrogen. If the sample is magnetic, neutrons can also determine its magnetic structure, namely the magnitude and orientation of the magnetic moments, or they can see the magnetism of a thin layer at the surface. Several neutron techniques can be used to study nanomaterials. Small-angle neutron scattering, or SANS, studies large-scale objects and lattices, typically from 10 to 100 nanometers. Neutron diffraction yields the atomic organization at the scale of the unit cell, from 0.1 to 1 nanometer. Reflectometry is sensitive to depth profiles at the nanometer scale, and radio-tomography images the inside of the material. In a SAN spectrometer, a monocynetic neutron beam, possibly polarized, is collimated before reaching the sample. Wavelength and detector distance are adjusted to select the appropriate range of the scattering vector, depending on the typical length scale to probe. The neutron pattern of an assembly of nanowires, taken with a neutron wavelength of 20 angstroms and a sample detector distance of 18.5 meters, is shown as an example. SANS is used to study the shape and evolution of objects hidden in the material. On the left, the influence of stretching in a nanocomposite. The nanoparticles inside elongate and the neutron pattern becomes anisotropic along the stretch direction. On the right, the contrast variation technique yields the nanostructure of grafted gold nanoparticles by matching either polymer chains or gold particles, or without matching them. The scattering curves provide the sizes of the gold core and of the polymer crown. In type II superconductors, a magnetic field enters inhomogeneously, and the superconducting currents create vortices along the field direction. When the field is aligned along the neutron beam, one observes the Fourier transform of the vortex lattice on the detector, yielding the periodicity and symmetry of the vortex lattice. For instance, if the lattice is hexagonal as in niobium selenide, the pattern consists of 6 spots on the detector plane. On the contrary, in YBCO, where vortices are pinned by twin planes, the twin domains yield 2 sets of 4 spots, misoriented by 45 degrees. In a diffraction experiment, a monochromatic neutron beam is diffracted by the sample and collected on a detector. The intensities diffracted by a polycrystalline sample are averaged over the Debye-Scherrer arcs, yielding the powder neutron pattern. From it, one can determine the atomic positions, site occupancies, magnitude and orientation of the magnetic moments of the atoms in the unit cell, as well as the lattice and magnetic periodicity through a simple Fourier transform. From the shape and width of the Bragg peaks of the powder pattern, one can also determine the typical dimensions of a nanoparticle, as shown on the left by simulations for a hexagonal particle. In magnetic manganese oxide embedded in Vicor glass, the confined geometry affects both the crystal and magnetic domain sizes. Neutrons can be used in reflection geometry to study polymer films at solid-liquid interfaces or in magnetic films. The measurement provides a depth density profile with a few nanometers depth resolution. In this example, the fit of the measured reflectivity, the black dots, allows reconstructing the width of the interface in a polymer brush grown with half deuterated and half hydrogenated parts. The interfacial region between the hydrogenated and deuterated parts extends over 25 angstroms. It is possible to perform radiography and tomography using neutrons. Neutrons are especially useful when studying light elements, such as water or hydrogenated materials in heavier matrices. They are also penetrating in heavy elements such as steel or lead. The typical spatial resolution is around 100 micrometers. Examples of such studies are soot deposits in filters, hydrogen loading in metals, studies of archaeological artifacts, and water uptake in porous materials.